All right, another round of applause for our Lido finance friends, Vasily and Andre. Woo. So I think in January, I was like researching crypto and Cosmos, and I would always talk to my girlfriend about it. And then she sat me down one day and she's like, I don't care. You need to find friends to talk to about it. So I made a Twitter account called Coney Daddy, and things have gone really, really well. Look at all my new friends I get to talk to, and you guys actually understand it all, more so than I do. Fantastic. Well, a new friend that I made this week, he's the co-founder of Celestia, Ismail Coffee.
Hello. First of all, I want to thank the conference organizers again for this awesome event. So nice to meet all of you in person again. I'm Ismail. I'm going to talk about Celestia and how it brings scalable shared security to millions, potentially millions of blockchains. First, a few words about me. I'm the CTO and co-founder, as Coney Daddy already said, and I used to be also a Tendermint core engineer. Before that, I was a research engineer at EPFL, where I tinkered with blockchain scaling, privacy enhancing technologies, and consensus and all distributed systems. You can find me on GitHub and on Twitter, on Liamzi, Kreuz and Quer. So let's dive in with what is Celestia. It's a modular, scalable security layer, or a blockchain stack. And why should you care? Because it makes it easier for you to deploy your application-specific blockchain. With the thing that it removes is the requirement that's currently there that you have to deploy your own consensus network. So if you want to deploy your application-specific chain, currently you of course have to bootstrap a proof-of-stake network, right? And we removed this, and you can more frictionless deploy your own decentralized blockchain. So let's start with something that most of you probably know, or many in the audience are familiar with the abstraction layers in Tendermint. Tendermint already does something really nice. It separates consensus from execution. So the execution you could think of like a transaction that modifies account balances. And how this is achieved in Tendermint is there's a thin layer called AVCI, and the state machine is a separate software layer. It could also run in a separate process, but it's still on the same blockchain, right? What we do at Celestia essentially is we take this monolithic blockchain architecture where everything runs on one chain, like consensus and the execution of the transactions, to a more modular stack. So in our case, the base layer, Celestia, just does consensus and provides security, and you can put the data on there. And on top of that, you can plug your application-specific chains. Don't have to run your own consensus. You could even have something that runs smart contracts on top of that. Yeah, and then in the traditional world, this would be all in one chain, as I said. So this is comparable to you can draw an analogy to the evolution of the web here, because if you look at the early web, the only way you could deploy your web application or your website was you have to host your own physical server essentially. And then the next step, the next iteration was basically you have websites that you can deploy using shared hosting providers. But these shared hosting providers would choose the programming languages you can use, the interfaces and everything. So you would be kind of stuck with the choices that the service provider did for you. And In the current web, websites run on virtual machines, so you have your complete freedom on like how you host your website. And similarly, we believe that the blockchain space will evolve, or already is evolving actually. If you look at the first cryptocurrencies, they were one like application essentially. And each blockchain, like Bitcoin, Litecoin, and all of this, had their own blockchain and their own consensus. The next iteration was like Ethereum, where you could deploy your smart contracts on one execution layer, essentially. And we believe the next iteration of that is a modern crypto ecosystem that's actually, to a great extent, already a reality, thanks to like Cosmos, essentially, where applications run on their own app-specific chains, but what's missing is like a shared security layer. And we believe that's the next iteration. So how do blockchains actually work? Current blockchains usually couple consensus with state execution, as I said. So for a full node to validate if a block is valid, what you make sure is a block has consensus, and then you actually also verify each transaction and execute those. So you check if the block has consensus, and you check if the transactions are valid, right? This is like a bottleneck because every full node has to execute every transaction. Yeah, and Celestia changes this to the design of Celestia basically is the answer to what if you can like post arbitrary blobs to the chain, and they do not modify the state. So you can even dump like invalid transactions onto the chain without having any impact. These would just be ignored, right? And like, how does execution work? Nodes and clients can actually download these transactions and execute them locally. That's the basic idea, right? It's actually interesting, like an interesting historic fact about this is that in the very early days of Cosmos, Jay and Bucky had a very similar idea, which was called Supertanker, where you basically would dump the other chain's transactions on the hub. That had several problems. I'll explain a bit more of this later. So that's what, because of these problems, the hub is what it is today instead of this. And Celestia has some answers on like how to do this properly in a decentralized way. So what like Celestia does is also it asks like the block, does it have consensus, right? Like as before. But instead of checking if the transactions are valid, you just make sure that they are available, so that they were published to the network and they are available for like full nodes to execute. Yeah, that's basically it. And so how do you make sure that the block is available? I mentioned before that like if you dump many transactions of like your millions of blockchains essentially on the base layer, the block can become potentially very large. And if you think of like the Bitcoin scaling days, for instance, there was like a big debate about like small blocks, big blocks, and like how big blocks create centralization. And in Celestia, we fix this, or like there's a solution to this in Celestia, which is called data availability sampling. It's a technique that enables you to make sure that the full block with all the data and all the transactions was actually published to the network without having to download the block. Sure, if you download the block, it's easy, it's trivial to make sure it's available because you downloaded it and you can verify the block. But what if you just like could download a tiny portion of the block instead and get like very high probabilistic guarantees that the full block is available. And that's what like data availability sampling enables. How it roughly works, I won't go into details, but like how it roughly works is how you lay out the block in shares, and then you erasure code these shares. And erasure coding is a very simple technique known since like I think the 80s. And this erasure coding and this block layout essentially enables what I said before, that you can download really just a tiny portion of the block and have like almost 100% certainty that the full block is available. Why is this interesting? The cool thing about this is the more nodes you have in the network, the more data you can basically host securely, right? So you get similar scalability guarantees as in BitTorrent. And BitTorrent is like the most scalable decentralized protocol that was deployed so far. So this is like very, very interesting. We're trying to bring that scalability of BitTorrent to the blockchain world, essentially. Like just to summarize again, the execution model is that applications use Celestia just to store the data, and the full nodes of Celestia, the main chain, do not process these transactions, right? The data is then processed locally, as I said. Well, that could raise the question, what if you have like light clients, for instance, or like nodes that cannot process all these transactions, right? Like if you have a light client, you don't want to download even your application-specific transactions. And the answer to this is you can solve this with like light clients and a rollup. What is a rollup? A rollup is like, they're quite hyped in the Ethereum ecosystem, and they're not like very much made it into the Cosmos ecosystem, and we will change this. So a rollup is essentially a blockchain that posts its blocks onto another blockchain, right? This is basically what I said before. Instead of the transactions, now you post the block, including a state root, and that makes your application-specific chain a rollup, essentially. There's two kinds of rollups. There's ZK rollups and optimistic rollups. We're currently focusing on the optimistic case, but something like Celestia is necessary in both scenarios, essentially. Yeah, in optimistic rollups, you need something for light clients to make sure that, that the block is actually valid, because you only receive a header, and the block proposer, the block producer, could essentially also be just a centralized sequencer, which is currently in all Ethereum rollups is mostly the case that there's just centralized sequencers. How do you make sure that they do not just post invalid blocks? How do you ensure that? By state fraud proofs, essentially. Like in ZK rollups, it's not necessary, because in ZK rollups you have a cryptographic guarantee that the state is actually valid, right? That's the only difference. People confuse this often. That's why I'm mentioning this. Another technique we're using, so like I said, all the applications, right? They post the data onto the Celestia main chain. How do you ensure that the application-specific chains only need to care about their application-specific data, right? The technique we use is a namespace Merkle tree. You could think of like a Merkle tree, a binary Merkle tree that is like domain separated by namespaces. So they're sorted by namespaces, and that enables clients to download their specific application-specific chunk of data. You could think of it like, from a tenement perspective, think of it as like a multi-tenant tenement, essentially. Okay, but like, I don't know if I confused you so far or not, but like, how do we actually get to millions of blockchains, right? I think, so what Celestia does, it reduces the barrier of entry, and like, you don't have to deploy your own proof-of-stake network. But I think you have to lower the barrier on all levels as well. So we need to do more in, we need better tooling, and we need better documentation. That's, I think, key to achieve this goal, independent of like the scalability technique, like Celestia, that would enable millions of blockchains. In theory and practice, we need better tooling for this, and better like developer usability. I think we can learn a lot. As the Cosmos ecosystem, we can learn a lot from Ethereum here, because like the tooling there is great, and the documentation as well, and we improved a lot, but there's still a lot to learn, I think. So what are the challenges we are facing specific to Celestia, and where we could have like, we could need some like community input and some interesting challenges if you want to work on those. One thing I mentioned briefly are state fraud proofs, right? Like we need those for like rollups, these application-specific chains. If you connect them, for instance, to each other, or just for light clients, you need these state fraud proofs. Originally we wanted to focus on like Cosmos or SDK based application-specific chains. We realized that it's actually quite difficult to have state fraud proofs in the Cosmos SDK, essentially because it's very, the Cosmos SDK itself is very unconstrained and not very, very well specified, and it's also constantly changing. So this is one challenge we're looking at, and I think here we could use a lot of help in like very clearly defining the SDK and its modules and defining a set of constraints how to make the Cosmos SDK state fraud provable efficiently. So this plays into the next step, like where I mentioned also you need state fraud proofs for rollups, right? And for rollups, it's even more tricky because if you think of, you have two chains, they're connected via IBC, and imagine like there's a state, like there's an invalid state on the on one chain, and you are connected to that one chain. You need a way to execute the transactions of the other application-specific chain, right? So you need, additionally to the efficient state fraud provability, essentially what you need is a default execution environment where you can easily take another application's state machine and run part of it. So that's easy in like smart contracts, but very challenging for like the Cosmos SDK as well, because like it's basically Go code. You can do whatever you want, right? So yeah, that's a very interesting challenge, and we're looking into the EVM as a potential solution to that. And we're also talking to Fede and Evmos. We're looking into making the EVM essentially more state fraud provable. And like many other teams, we basically need ABCI++. We're very hyped about this. Actually, we had an implementation of the first phase of ABCI++ long before it was actually fully specified. In fact, I don't want to take any credit of this. In fact, but like I told Dave that why not? It's actually odd that you only have like ABCI callbacks to the state machine in the last phase of the consensus. Why not have them in all phases? And that's what basically ABCI++ is. So we needed to modify the block before we're proposing it to separate the state relevant portions from the blobs essentially that I mentioned before. We're eyeballing with immediate execution instead of the deferred execution model that Tendermint currently has, where like the state root is the state root in block n represents the transactions of the previous block n-1 essentially. Another challenge we face, so what I mentioned, data availability sampling, is quite, it has much more requirements and like much more challenging requirements to the peer-to-peer layer. So we are looking on internally pushing to move to the P2P. So our stack is based on the P2P and parts of like IPFS, and we also trying to push for Tendermint itself to move to the P2P, and we're potentially collaborating on this with Protocol Labs and Interchain GmbH and Informal. And if you're interested in like in P2P work, please come talk to us later as well. And another thing that we faced is that Tendermint is although it's like an awesome piece of software, it's not as easy as it could be to swap out certain components in Tendermint without having to maintain a fork, right? So it's like we Merkleize the block differently, we do the erasure coding, and yeah, again, it would be nice if the peer-to-peer layer was easily, it was easier to swap out the peer-to-peer layer, because like this is currently quite intertwined in Tendermint. So that brings me to the end of my talk. So to summarize again, we are building the first really scalable, modular, universal consensus and data layer that brings shared security. And it will enable developers to develop to deploy their own application-specific chain without having to deploy your proof-of-stake network. And we envision long-term that this will enable global communities that can self-organize using decentralized networks and tools without being burdened by existing power structures. You can learn more on our homepage, and I don't know if I still have time on questions or not. There's 1 minute left if you have questions, but we have a booth, and Nick, a colleague of mine, and me, we're there. Please ask us all questions that you have, and come talk to us as well. Thank you.
Ismail, thank you so much, man.
Thanks, man.
Well done. Well done. All right.